All right, so you were looking for a little bit of extra assistance, I guess, with going through and dealing with re-expression. So the following is a whole explanation using one particular example of how to re-express. It's going to take you a while to go through, and I decided not to put myself in the bottom little corner because really, it's bad enough you got to listen to me. Do you really want to see me too? All right, have fun. All right, so we're having a little bit of difficulty when dealing with re-expressing data. So we have this particular example of population growth in the United States. Here we've got the year starting with 1800, ending in 2000, and the population in millions of people. So when we go through and start looking at data sets along these lines, I want to try to come up with a model so that, dependent upon the year, I can predict what the population would have been. Normally, as we know from just our Algebra 2 experience, population growth is usually exponential. But I'm going to try to make it so that I have a linear model to predict population in millions. In order to do this, let's take a look at a couple of the assumptions first and foremost, because I don't want us to forget that we need to do these checks every single time. So as we scroll down, linear relationship assumption, quantitative data condition. Both years since 1800 and population in millions are quantitative variables, so therefore that condition is met. The straight enough condition. There's no way to know that right off the bat, so I'm going to have to go through and create a scatter plot, and we'll do that using the graphing calculator. But knowing our intuition, if you will, of dealing with population, I don't think this is going to be straight. So then we're going to look through and take a look at the outlier condition. Again, we're going to need to look at the scatter plot before we can even go with discussing that. Equal variance. There's only one way to really determine whether or not we have equal variance. Remember, before we can even check equal variance, we have to have met the linear relationship assumption. So if we can't assume a linear relationship, there's no reason to even consider equal variance. Once we know that we have something that is roughly linear, then we can go ahead and investigate here. Once a linear model is created, that will provide us with a series of residuals for each of the x values. Then we want to take a look at the residual plot. If we don't see a pattern in the residual plot, then we can assume equal variance. Alright, so now we're taking a look at what the graphing calculator would give us. I've already gone through and I've entered into the lists what exactly we're looking at with our data set here. So I have 1800, 1825. I put these in like this just to start. Left list 2 blank, have list 3 here, just in case I have to go through and do any adjustments to list 2. And then, of course, we have list 4, 5, 6, so on and so forth. So what I'm going to do, though, is we usually start it as, where our lists are years since 1800 for this particular example. So what I'm going to do is I'm going to go into my regular, just normal screen that we see. And this is a good opportunity to figure out, okay, well, how do I modify a list? How do I get the calculator to do it? Because I don't want to retype everything in. So I have everything in list 1. So if I take list 1 and I subtract 1800 from every single element there, then what I'm going to get is I will get my years since 1800. So I'm going to take then, I need list 1, which we do by second 1, and I'm going to subtract 1800 from that. And I'm going to store, which is the STO, store that into list 2. Enter. So there are all my values. If I don't believe that that's what it says and that that's what I'm looking at, then I just go ahead and ta-da, there they are, right through here. Alright, so I know based on what I had before and what we were looking at in the presentation piece, I've got to check to see if this is actually straight enough. Alright, so let's take the list 1 and we'll take list 3, and then let's go ahead and create a stat plot. Okay, so here we are. We're in our normal, second y equals gets us to here. Now I'm going to want to hit enter so that I can take a look at this one. So let's turn this one on. It's already set for a scatter plot. I'm going to use list 1, and then I'm going to arrow down and use list 3, because remember that's where I put my y values. And then notice how this turned back to something that could be useful. Before it said error. So now we're going to come up here, we're going to zoom. We're dealing with statistics, so we got to deal with 9. Alright, so now I'm looking at these data here, and they don't exactly look linear. So I'm not even going to go through and create a model for this, because my creating a model for this, then I'm assuming that they're linear. What? This does not meet the straight enough condition. Not even close. So then, you know, the outlier condition I don't have to worry about because I don't even meet the straight enough condition. If I don't meet the straight enough condition, I don't meet the linear relationship. If I don't meet the linear relationship, there's no reason to deal with equal variance. So what we did in my example kind of was extraneous. It was extra work. There was no reason to do that, but I wanted to make sure that you saw through the residuals that this was not going to work. So now where do we go from here? What do I do? Well, we take a look at the ladder of powers. Okay, so here's my raw data. This is where I am normally, where we don't have to change anything. So if I move through these ladders, so I look here, so if I move up, I take the square of the data values. Well, this will work with unimodal distributions that are skewed to the left. Well, recall that mine actually grows exponentially. It's basically an exponential function. So it doesn't meet this requirement, so then I'm not going to go up. I'm going to try here. Let's take the square root of these data. So I'm going to go through, I'm going to take the square root of them, we're going to go back to the calculator. Now if that doesn't work, I might need to move this way and keep going down. Okay, so maybe we need to use logarithms. Okay, that's measurements that cannot be negative often benefit from a log re-expression. Well, if I'm dealing with population, I'm not going to have a negative value. So, but I'm not going to move straight from here right to logs. Okay, I don't want to go from raw data to logs. I want to move my way through the progression. And that's what we'll do next. Alright, so we already know from the stuff that we've done that just using list 1 and list 3, that's not going to help any. Now what if I go through and I use list 2 and list 3? Would that change anything? Well, upon further investigation, remember that when we change the scales, it's not going to change the relationship. So really moving from list 1 to list 2, it's not going to do much of a difference. Okay, it's not going to have a graph change. It's still going to look the same. So what I want to do then is I want to do a list 2, and then we need to do some adjustments to list 3. Now remember, from the ladder of powers, I want to go through and take the square root of my y values, or my population. So here's another example of when I can go ahead and put the information that's here, take the square root of it, and drop it into this one. So let's go back to our main calculation screen. I'm going to take the square root, which remember is second x squared, of the list that is list 3, which remember is my y value. Get out of that now, get out from underneath the square root. Then I'm going to store that into list 4, which is just do second 4. Hit enter. So there are all the values. Now if I go back into my lists, go ahead and hit edit, there's list 4. So what we've done is we've taken the square root of all these values. Okay. So now let's go ahead from there. We're going to create a scatter plot. We'll use list 2 and we'll use list 4. So now we're going to go back into scatter plot. We're going to deal with plot 1. So let's just go ahead and get into this one. We'll turn it on. Arrow down. I am no longer using list 1. I'm actually using list 2, which remember, it doesn't really matter. It's not making a difference here. And then we're going to put our square root of the entire list here. So this is our re-expressed data set. Okay. Now I'm going to want to go through and zoom 9 so I can see what it looks like. All right, well, that's better. Remember, there is no best model, but that's a better looking model than the other model I had. This one I think would be a good idea to go ahead and take a linear regression and find out. So let's see, we'll hit stat, we're going to calculate. Remember, this is number 8. I know this is getting boring where we're hitting the same thing over and over again, but that's okay because it gives us more practice. So we have list 2 is where the x values are going to be. List 4 is where the newly re-expressed values are. And then I'm going to want to again go in here, get my variable, get my y variable. We'll put it back into y1. And then we're going to go ahead and calculate it. So here are the values for my linear regression. Now remember before, I had a strong R value, yet the R value means nothing if I do not have something that even looks straight. So in this case, it's definitely straight, I should say, than where we were before. But there's really only one way to test to see if this is going to be an appropriate model or not. So where do I go? Well, it looks like it's straight enough. I don't see any outliers here. So then let's take a look at the residual plots. So now I got to go back into y equals. I want to turn this plot off. So now that one's off. I don't have to deal with that. Go back into y equals. We're going to turn the second one on. And we're still going to deal with the residuals. Remember, since I did a new graph, I now have, a new linear regression. I have new residuals. I'm going to grab my list 2 because that's where my x values are. I'm going to ask it to, well, I got to turn this thing off, this equation. So let's go back into y equals. Turn this equation off because I don't need the line. It's just going to get annoying. Then we'll go through and we will zoom 9. Uh-oh. Why didn't it do anything? Well, because I still need to turn that one on. So let's go back into y equals. And these mistakes that I'm making are actually a good thing. Why is this a good thing that Maine's making errors? Well, because this is the kind of stuff you're going to do. You're going to make these little errors. You're going to forget about where things are, and you're going to have to be able to go with the flow here. All right, so zoom 9 again. There's my residual plot. All right, so I'm trying to figure out if there's an appropriate amount of scatter. It's kind of difficult here. I mean, if you look, I've got the middle section is low again. I've got 2 values that are over here that are high. I've got one that's here that's high. I've got one right on. Well, that's pretty cool. And then I've got these below again. So it kind of follows a pattern, but not as bad as the other one. Well, then let's try to re-express again. Maybe I can find a better model. Alright, so we did the square root counts that often benefit from a square root re-expression. So I didn't have counts. Well, no, I really did have counts. I had counts of the number of people that were around. So that might or might not have re-expressed it enough for me. So now we're looking at this here. Measurements that cannot be negative. So now we're going to take a look at logarithms. And we're going to go through and re-express the y values, or basically the population in millions, to see if that gives me a better model. Alright, so here we are again, back into our lists. So remember here, list 1, these were the actual years. List 2, these are the years since 1800. List 3, this is the population in millions. List 4, this is the square root of the population in millions. Well, we need to see if going through and now dealing with the log of population in millions make it any better. Alright, so that's going to be my list 5. So now I'm going to do second, quit, get out of all that stuff. And now I'm going to go through and I'm going to take my list. Well, first off, I need to take the log. So log of the list. So let's see, that would be list 3. Close my parentheses, and we're going to store that into now list 5. And again, just hit enter and it'll ding ding ding, put everything where it needs to be. If you don't believe me, again, go ahead and edit. Now this is the log of each of these, okay? And log base 10, you can use natural log, but really it's not going to be a difference. The reason we use log is because we're in base 10. Natural log is a completely different base. It's known as base E. There's no way, not even no way, there's no reason to even use that. Here we're going to turn on the scatter plot again, so it's the same process over and over. Okay, so list 2, we're good. Change this one. List 5, that's why I have everything in a different location so I don't have to worry about it. Go ahead and hit enter. Everything's where it needs to be. So now let's graph this thing. That one looks like it almost bends it the other direction now. So I'm going to create a linear model here. I don't think that this is really straight. It looks like it curves the completely other direction. So then we've gone too far. If you get a data set that started like this, and then you change and bend it more, then you've gone too far. So I think we've gone too far. So now we go back. We're going to go back to the other one. All right, so now we have a model. Let's go back to the original equation. So here's the information that we were given. And if I look, okay, here again, my years, my population in millions. So then as we progress through, we talked about the linear relationship assumption. We already knew that we had met the qualification of quantitative data. So now we're going to look at straight enough. Well, we looked at first and we said scatter plot wasn't quite straight enough. So then we re-expressed. So we re-expressed these data. And basically we went through and re-expressed the population, the square root of population. There was still a slight curve, but it was straight enough to fit a line to it. Then we went through and tried re-expressing using the log of the population, which then overcompensated for the bend, and we went too far. So therefore the better model was to go through and go back to the square root of the population. Now when we look at our outlier condition, it did not appear that there were any, so therefore we had to just continue. And then when you looked at the equal variance, then as a result, we see that, even though there's a slight curve in the residual plot, the residuals themselves are quite small. So when you look at your line that's fit to the curve when we did the re-expression, it's actually not too bad. So then let's take a look at what our model came out to be. So this was from using the square roots. Notice that we have a strong linear association here now once we've taken the square root. Our r squared is rather large, and we come up with this as our model. So the square root of the population hat is equal to blah. You can read the rest. So now, is this model appropriate? How do I check appropriateness? Well, remember, appropriateness comes from the residual plot. So yes, based on the residual plot, even though there's still a slight curve, the residuals are actually quite small. So it's okay to proceed. Now, will the model be accurate, though? How do we get accuracy? Well, accuracy, remember, we've got to take a look at our r squared. So remembering that, these models are useful, but there are no right ones, this model would be fairly accurate. R squared for this model is 0.993, so 99.3% of the variability in population in millions can be accounted for in a variability in years since 1800. That leaves very little variability in the residuals. Alright, so based on this model that we've created, what would the population have been in 1968? Well, we have to substitute 168 into the equation for the year. We attain a value of 13.97. But remember, this is the square root of the population in millions. Here's where most of you will make small errors. You'll just stop. Well, don't forget, I've got to square that so I can get my population. So based on this model, we would expect the U.S. population to have been around 196 million people in 1968. Obviously, there are ways to check. We could go through and find out. Would your model be accurate for the year 2001? Well, what about 2050? Well, 1 year beyond, we would still be pretty accurate. I mean, taking a look at it from 1800 to 2000, I go 1 more year. Yes, we are extrapolating, but we would still be fairly accurate. However, the model was not designed to predict much more beyond 2000. So it may be accurate for 2001, but it definitely will not be accurate for 2050 because we've extrapolated. So we are not allowed to extrapolate or go beyond the model. So therefore, it might be okay for 2001, definitely will not have much reliability as we sprawl out to the year 2050. All right, well, I hope that this very long, drawn-out explanation helps somewhat with dealing on re-expressing data sets so that you can go ahead and create linear models. Thank you, and good night. Hey, wake up. It's over. You can shut down now. All right, bye.